North of New Zealand, the Tonga-Kermadec Trench, as well as the Tonga and Kermadec Islands, result from convergence between the Pacific and Australia plates. This subduction zone lies along the southwestern part of the circum-Pacific Ring of Fire. The region has surprisingly complex tectonics that generates volcanoes and a variety of earthquakes, ranging from deep subduction quakes to shallow great earthquakes that produce tsunamis. The Pacific Plate subducts beneath the Australia Plate along the Tonga-Kermadec Trench. If we consider the Australia Plate to be immobile, the rate of motion of the Pacific Plate towards the Australia Plate from south to north increases from 46 to 84 millimeters per year. As Pacific Plate lithosphere dives into the subduction zone, it produces earthquakes of increasing depth from east to west. Viewing the earthquake distribution in 3 dimensions, we see the maximum depth of earthquakes is greater in the Tonga than in the Kermadec subduction zone. Using earthquake depths, we can plot contours of depth to the top of the subducting plate. In the Kermadec Trench, the Pacific Plate subducts into the hot mantle at a rate of 50 millimeters per year, and earthquakes are limited to less than 300 kilometers depth, because at deeper levels, the plate has warmed and is no longer brittle. In the Tonga Trench, the Pacific Plate subducts at a faster 76 millimeters per year, so the subducting lithosphere reaches 700 kilometers depth while still cool enough to be brittle and produce earthquakes. Adding active volcanoes shows the line of volcanoes along the Tonga-Kermadec volcanic arc. On January 15, 2022, just 70 kilometers from the capital of Tonga, the explosive eruption of Hunga Tonga-Hunga Ha'apai blasted a volcanic plume 58 kilometers, or 36 miles high. It was the largest volume volcanic eruption since the 1991 eruption of Mount Pinatubo, and it released more energy than any eruption since the 1883 eruption of Krakatoa. The pressure wave and possible additional sources, including submarine landslides, generated a tsunami, with waves up to 20 meters high locally, that reached as far as Japan and the Americas. Only about 5% of tsunamis are generated from submarine volcanic activity. The back arc region is important to understanding the Tonga-Kermadec subduction zone. Marine geophysical research has documented how back arc rifting and spreading split the former volcanic arc to produce the Avre Trough and Lau Basin. To examine this tectonic history, let's again nail down the Australia Plate and rewind Pacific Plate motion back in time. 6 million years ago, the Louisville Seamount chain was east of the Tonga Trench, and the Hikurangi Plateau was east of the Kermadec Trench. From 6 million to 4 million years ago, rifting split the entire length of the volcanic arc from New Zealand to Tonga. At 4 million years ago, the Louisville Seamount chain enters the Tonga Trench, and the Hikurangi Plateau contacts the Kermadec Trench. These high-standing features on the Pacific Plate scrape along the bottom of the overriding plate, slowing or stopping back arc rifting. By 3 million years ago in northern Tonga, the Louisville Seamount chain has subducted below the overriding plate, and back arc spreading starts in the northern Lau Basin. As Louisville Seamount chain subduction sweeps southward, back arc spreading initiates further south, and the Tonga arc rotates clockwise like a wiper blade, with spreading faster in the northern than in the southern Lau Basin. GPS observations from 3 stations on Fiji and the Lau Ridge and 3 stations on islands of northern Tonga document continued east-southeast motion of the Tonga arc at rates increasing northward from 91 to 159 millimeters per year. The subduction rate at the Tonga Trench is Pacific Plate motion with respect to the Australia Plate, plus motion of the Tonga arc away from the interior of the Australia Plate. Pacific Plate subduction into the northern Tonga Trench reaches an astonishing rate of 240 millimeters per year, the fastest rate of subduction anywhere on Earth. At the northern end of the Tonga Trench, the Pacific-Australia Plate boundary changes from a north-south oriented subduction zone to an east-west oriented transform fault. At the Tonga Trench, the Pacific Plate subducts beneath the Tonga Arc and Lau Basin. North of the corner, the Pacific Plate slides west along the left lateral Fiji fracture zone. Seismicity in the region confirms that deep earthquakes do not occur north of the Fiji fracture zone. Seen in 3D, the contrast is even more impressive. Looking north along the trench, we see the brittle Pacific plate diving to produce deep earthquakes. If we rotate the 3D view to look east, we see deep earthquakes are only found south of the tear fault. This plate geometry indicates that as it encounters the northern end of the Tonga Trench, the Pacific plate is tearing into a southern subducting part and a northern part that remains on the surface. Unusual earthquakes with south side down displacement on vertical fault planes document this tearing of the Pacific plate. Given the extremely fast rate of subduction of the Pacific plate at the Tonga Trench, we might expect this plate boundary megathrust to generate frequent major and great earthquakes. Over the past 50 years, there have been 36 major or great earthquakes along or near the megathrust. But fault displacements during these earthquakes amount to a small fraction of the plate motion. The majority of interplate motion across the plate boundary occurs by continuous slow slip along the megathrust boundary, not by earthquakes. This indicates low friction, probably because the subducting Pacific plate is old, cold, and dense when it enters the trench, and is pulled down by gravity, lessening friction on the plate interface. Nevertheless, 7 great earthquakes have occurred along the Tonga Kermadec plate boundary since 1900, with the 1976 and 2021 Kermadec events documented as interplate megathrust events. Because of the potential to produce tsunamis as well as ground shaking on nearby islands, shallow great earthquakes pose significant hazards to the region. As the subducting plate bends to descend into the trench, the top of the plate is put under tension that can produce normal faulting earthquakes. At 6:48 a.m. on September 29, 2009, a magnitude 8.1 normal fault earthquake originated 12 kilometers beneath the seafloor. While the fault rupture was still progressing, the normal fault earthquake triggered a magnitude 7.8 thrust fault earthquake on the plate boundary megathrust. Then, a second magnitude 7.8 thrust fault event was triggered 91 seconds into the earthquake sequence. 350 millimeters eastward displacement of Niautoputapu Island as seismic waves swept past provided further evidence for the megathrust displacement. This 2009 Samoa sequence is the first known example of an outer rise earthquake triggering a major thrust fault earthquake on the adjacent subduction zone plate boundary. The resulting tsunami wave train had a leading trough, or depression in sea level, moving northeast, and a leading crest, or rise of sea level, moving west. So when the first waves arrived about 13 minutes after the start of the earthquakes, the ocean receded from the shore in Samoa, but advanced onshore in Tonga. Successive waves rushed onto and away from the shores, causing 189 fatalities and over $200 million in damage on the islands of Samoa and northern Tonga. On Upolu and Samoa, tsunami run-up reached over 11 meters at Lalumanu, where the village was completely destroyed. 143 fatalities occurred on this island, with low-lying coastal plains requiring long evacuation routes to reach high ground. Run-up reached 17 meters on western Tutuila Island, and the geometry of the harbor at Pago Pago amplified tsunami run-up to 8 meters, with inundation more than 500 meters inland. Because many citizens evacuated to high ground upon feeling earthquake ground shaking or noticing unusual activity of the ocean, only 34 fatalities occurred on Tutuila. In this region of tectonic complexity and widely dispersed islands, volcano, earthquake, and especially tsunami education and emergency preparedness are essential.